Thank you very much. Very pleased to be here. I want to give credit to the co-authors of this presentation, but Gary, due to a medical condition, will not be able to be here. Ian is here. Is Yoshio here? Yoshio's not here. Okay. What I say is I take personal full responsibility for anyway. Now, Jack, after your talk, I didn't really know whether I should come up here or not, because this is all I've got to offer. This is a life-size model of everything I'm going to talk about, which is a dust detector on the moon put there by Apollo 11. I'll show you a photograph of it. Three little solar cells, $100 a lot. Okay, so what I'm going to talk about is dust on the moon, and I get myself organised. If you can refer to the website there, please, www.brianjobrien.com. That's got a lot of discussion and a lot of references. So I ask that you go forward with that. This, of course, is a well-known LRO photograph of the Apollo 11 site, and you'll see the where the PSP and the rest were deployed, and we'll go quickly to the next one. Buzz Aldrin carrying the ESAP, the early Apollo Surface Experiment package. This was the only package specially designed for the quick one excursion EVA, where you could release everything with just the press of one hand. And that's the packages, and this is the 17 metres deployment distance. That's from, well, you can estimate it, look around the room and pick 17 metres and visualise a rocket taking off there. This is the complete scientific active package. That's the Apollo 11 took a couple of passive experiments, important ones, but I'm not going to talk about those. I'm only going to talk about the ones that were powered by the solar panels, which you see on either side, and then the data were transmitted back to Earth and taped and analysed and so on. And of that package of two active experiments, the 47 kilogram one was the passive seismometer, and that was by far the most important, but the little fella here was tucked in, just bolted onto that, and measured the dust that accumulated on 3 solar cells. And if there's dust on the solar cells, very primitive, you've got the sunlight bearing down, and the voltage out of each solar cell decreased linearly according to the amount of dust that was there. Say 10% for 1 milligram per square centimetre. Very, very primitive jacket, no equations. Okay, let's get down to the heart of the matter. If I may try to put this into perspective, the dust detector itself can rarely be seen except there. Now that's life-size there. And that's still up there. I'm rather pleased with that. This is an actual flight unit that was built for Apollo 15 and never flew for reasons unknown. This was found in the garage of Jim Bates at Houston a year or two ago. There are no close-up photographs of the actual Apollo 11 experiment, except that one in the Smithsonian. Now we get down to the nitty-gritty. If you go to the website, you'll see the actual film in which Buzz tells the story about he and Neil Armstrong, when they took off. Within a second or two, Neil said, "The flag is blown over." And they agreed then and there that there was no need for the public to be informed. Now, that is basically the same reaction I had in Sydney. I recommended in my first progress report on the 15th of August that there not be a press conference because we didn't want to rain on the glorious parade of Apollo 11. And that's the way people would take it. And that's been hammering it at us against ever since, Greg. Okay, I'll leave it to you to listen to Buzz on the website. So there's a list, a general desire not to rain on the parade. Dust is a nuisance. For geologists, dust is a nuisance as well. I heard a faint feminine laugh there, but still. Now, what I'm going to show you is that the preliminary science report, the Apollo 11 preliminary science report, SP 214, it actually starts its measurements after the lunar module took off. And yet it reported that there was no significant degradation. And of course, the very good reason was that the rocket had already gone. This is the NASA official SP 214. Okay. A little bit of philosophizing here because we didn't want to rain on the parade, but on the other hand, we urgently needed the truth. We needed to work out what distance Apollo 12 would be deployed at. Rather than 17 metres, it was 130 metres, and that was good. But there are 142 geologists, principal investigators, waiting to know if there was any disturbance. And if there was a disturbance from the lunar module ascent, there surely would have been disturbance from the lunar module descent. The lunar module ascent report said there was no significant disturbance. This is the actual measurement with the dust detector. The time scale here is every 2 hours. The three colours are the three different solar cells there. And as you can see, there was significant degradation at lunar module ascent there for all but one cell. One cell was 0, one was 17%, the other one was 7%. In the temperatures, the two solar cells, the two thermometers attached to the solar cells showed overheating. This one down here is the Belcom measurement of lunar surface temperature. That was a decrease. It's the only measurement that's ever been made of the effect on the lunar surface temperature of the ascent of a lunar module. This is young Ian's contribution to show that the measurements on figure 10.4 of temperature and 10.3 of voltage that are printed in the NASA preliminary science report for Apollo 11, they were actually as lunar module ascent. The first measurement was made on or about the lunar module ascent. Yes? So. But in fact, in comparison with the previous comparison with that, it was made after. Okay, see the tracks of the 3 solar cells. Simplest way to see it is on figure 10.3, that's the solar cells going up. Notice that there's equal difference versus, okay? So the preliminary science report, which reported and was then quoted on page 100 to say there was no significant disturbance, was wrong. The measurements were made after. So the main results are, we corrected that as soon as we could, but it was by October before we could, and nobody noticed. The measured degradation was the first and most important thing that we saw. The measured effects of the first rocket ascent from the moon, and consequently, as I said, Apollo 12 was deployed 130 metres away. And there is a point that I need to talk some more with Yoshio about. While working for this presentation, it looks to me as if one of the thermometers on the lunar seismometer is giving evidence, or gave evidence, that some of the debris, as well as dust, might have affected the bigger seismometer, which sounds reasonable. You see, this is one of the thermometers, and right at lunar module ascent, there's a sudden cooling. Now, you'd get cooling if you had shadowing of that thermometer. But the following behaviour is quite weird, and Yoshio and I are still working on that. Okay, so Yoshio's given me these as the numerous events of different appearances. Can you all read that okay? You can read it faster than I can say it. This is Yoshio's interpretation of the effects of seismic effects for Apollo 11, and also looking into the future. Okay. So much for that. I want to go to the future myself. And this is my suggestion for the mandatory inclusion of 2 different types of dust detector on every flight. We almost reached that decision at the Micro Symposium in March. In fact, it was agreed, but not quite in this detail. I'm proposing that there should be a fungible dust detector as per Apollo 12, my original invention, with a solar cell looking to the sun, sunrise there and up, and then on sunset. But the one that's of interest is the Changi 3. This is the sticky quartz crystal microscale. It measures the actual weight of or mass of the dust. And I put that up there because it's likely in the next few days, or may have almost happened, or the next week, that will be online from one of the Western journals. Had that cleared to put that up so that will become the second measurement ever made of dust on the moon. Thank you.
Okay, we have time for one quick question. Greg.
Brian, I just, first of all, I want to note that I think you deserve the prize for coming the farthest. Brian came from all the way from Perth, Australia to this conference. And second, I wanted to say thank you. We've known each other for 10 years. 10 years ago at the forum, we had a special panel with the ALSEP investigators, which I believe included you. And I wanted to just thank you for your pioneering work and the pioneering work of all the other ALSEP investigators. We continue to enjoy and use the data that you collected. So from the community, thank you very much.
Thanks, Greg. I'm afraid that there aren't too many of the first original 7 left.
Thank you very much. There you go. Okay. One more talk in the session. This is the U.S. National Near-Earth Object Preparedness Strategy and Action Plan, Summary of Progress to Date. And the talk is given by Victoria Andrews.
Thanks for adding me to your session. This is great. You've got a pointer. This is how you advance the slides. Okay, this one. Okay. I'll give you a hand signal at 5 minutes. Okay, great. Thank you. Hi, good morning. Thank you, and thank you for this sudden shift in topic. But if we refer to our friend the moon, as Clive Neal often does, as Neo Prime, perhaps you'll forgive me. And I also think of it this way. Once we have that outpost on the moon, remember that all those micrometeoroids that are so pretty flashing in the night sky here on Earth will be actual hazards to any lunar outpost. So at any rate, there's going to be a lot of words on the charts. You'll be able to refer the charts online, and I'm going to probably skip past a lot of the words and go to the pictures to explain what we're doing. I'm Victoria Andrews, used to be Friedenson, didn't get married. NASA finally let me change my name. Talk about bureaucracies. So I am now Andrews, and thank you. Planetary defense is the concept of looking for asteroids so that we can be prepared in the when-if event, one that is heading toward us. It's a full spectrum program, very small in the Planetary Sciences Division, in which we find them, track them, attempt to characterize them, anticipate them, and try and figure out what we would do in the event that when we find one that's headed toward us. Just a brief break. To date, we've, as of last Friday, we found 20,444 asteroids, 8,693 were 140 meters, what we are mandated by Congress to find, and larger. We track them every night. Results come in worldwide every evening and are added to the database. I've either gone forward 3, okay. Hopefully it'll stay. But just to give you a graphical presentation, it's taking us a while to find them because we're using primarily ground-based telescopes, which are, of course, limited by things like daylight. and bad weather. And at this rate, while we are making steady progress at this point, it's going to take us about 30 more years to find the ones that we are most interested in. 140 meters is a sort of a threshold in which we would understand that there would be serious consequences to an impact, no matter whether it was on water or on land, from an object that size or larger. So we have this action plan that was published by the White House in June of 2018, and why is it important? Well, for one thing is that it's understood that this is a very low probability within anyone's specific lifetime, high consequence event. And in understanding that, it behooves government or governments to at least have it in planning, not as something that's an active concern, like, you know, we're currently in hurricane season right now. And I know California is gearing up for another potential wildfire season. So it's a thing that governments have to prepare for. It's also, in many things, it's NASA's job to find them, but it's not necessarily our job to do something. Okay, so it would take, we propose, and which I think other agencies are agreeing to, it would take various federal agencies and entities to be effectively mount a response. And in something that was proven in 2015 with the Chelyabinsk meteorite over Chelyabinsk, Russia, and recently with several power outages, responding to hurricanes and wildfires, is that our engineered environment is in some ways fragile to natural disasters, in which it takes time and a great deal of money to recover from an event. So we would want to know about it so we can effectively prepare. But you just don't do it, you know, it's not don't know Bruce Willis. He doesn't come to our meetings, no matter how much we invite him. But at any rate, so it takes more than just finding them and going, oh my gosh, we got one incoming, guys. But it's also, we have to understand what the implications are of an object of that size. What do we know about it? What are our unknowns, okay? What haven't we asked yet? And then how to effectively communicate with other aspects of the federal government and even internationally. And then how, of course, how we talk to our public, how we talk to people about this, how worried should they be? How not worried should they be? So this activity actually started in 2015, working across the federal agencies through OSTP. We published the National Near-Earth Object Preparedness Strategy in December of 2016, and then we followed that up with an action plan in June of 2018. And NASA has been assigned the lead to work with the federal government on responding to the goals of the action plan. So there's just 5 of them, which is basically can be summed up as be aware and be prepared. I'm not going to read these. I'm going to skip over the wordy charts. I can answer any questions and tell you anything about the wordy charts later if you'd like. But under Goal 1 is the first obligation we have at NASA is to detect, track, and characterize. And so there is an organization through the Near Earth Observations Program that works worldwide, but we do have NASA-funded facilities here in the U.S. and some overseas in which data is taken, there are studies done, and it goes through a continuous process to vet the data, to provide grants through Rose's Calls and through SMD's RNA program to fund studies. So this is an ongoing activity, and we're looking at what we might do. For example, what are the upgrades to telescopes and other facilities that could actively implement and improve what we're doing today. Then there is modeling, predictions, and information integration. So in order to understand what would happen or what could happen if an asteroid is headed this way, it's actually very diverse communities well beyond the planetary sciences, space sciences world that would look at this. So it's first, what NASA knows how to do is find them, track them, and characterize them. Approximate compositions, approximate spin state, approximate, what can we get from either infrared or radar, if we can get radar on it. But then What would happen when it enters the atmosphere? That is a different community that does that, that looks at big objects going boom in the atmosphere. And then there is another set of communities that looks at what would happen on the ground to a disaster like that. For example, Homeland Security does a lot of analysis on things with massive sudden power outages. You think your power goes out, but what it can do is if there's a backlash, then the power really is out for a very long period of time. What happens to various facilities and things? What happens to the infrastructure? Could it cause a tsunami? These are all different entities, and for the first time a couple of years ago, we got all these communities into the room and get them to talk to each other. And what we're not proposing is to form a massive one-size-fits-all, plug in data here, get an answer there, but to have a grassroots, if you will, coalition of the folks who actually do these models and know each other and know that when we do have an asteroid and there is a warning coming in, that the various agencies know who to call and that there are folks working on it and we're not starting from scratch. Then what do we do about this? This is the Bruce Willis part of our talk, is looking at what we might do. So what we're looking at is designing a reconnaissance mission. With ground-based telescopes, we're not going to get all the data we need in order to effectively understand what we can do if there's one incoming. So what we're looking at is to identify, if you will, working to characterize what a recon mission looks like. What's the de minimis set of data that you need to effectively figure out what your next step is, and what does that spacecraft look like, and how much time do we need to build that spacecraft? How can we develop a rapid response capability to get spacecraft out there? And then secondarily to that is to look at how we can rapidly develop spacecraft that can mitigate through deflection or disruption an asteroid that's on its way. Of course, the longer warning we have, the more options we have, right? So we conducted, through the Planetary Defense Conference in the spring of this year, an exercise in which there was a smallish object that was headed and we needed to do something. And the analyses showed by these communities that it would take 10 launches of kinetic impactors in order to keep moving this object away. Well, okay, now just you all know about missions and how it is to fly missions. Think that through, how we're going to get 10 spacecraft built in a very fast period of time. So one of the things that Planetary Defense has got is the DART mission being built at Johns Hopkins University. She'll launch in July of 2021 right now, and will travel to the Didymos asteroid system. Didymos is a binary, and we'll attempt to, by hitting the Didymos B, or the Didymos moon, hit it and move it, okay? And we'll be able to track that, and that will be the first effective test of a kinetic impactor. There are other things that we also look at how you could possibly move an asteroid off Earth. Looking internationally, we can't do this alone. Even if the asteroid was proposed to impact somewhere else, we would be working internationally, and this was over just after Christmas Day this year, and through international cooperation, we got data from other entities, Japanese spacecraft, to understand this very large bolide that came in just off the North Korean peninsula. And finally, how do we work in an all-of-government capacity? So when there is a disaster in your area, you hear about FEMA, right? But it's actually other agencies and organizations that come together to bring all this capacity to bear in order to respond, like with Northern California's wildfires. So we're working very closely with FEMA to understand what they need to know. So that was a very big talk in a very few minutes, but I wanted to end with this one in case you have questions. These are all the asteroids that have been, these are the actual orbits of all the asteroids that we've found so far. And it's a very small fraction of the total population. So there's a few things out there. But NEOPRIME keeps doing its work to clean up the skies for us. If you look at the history of the impacts on the moon, you realize that if it impacted there, it didn't impact here. So thank you very much for your time and attention. I look forward to if you have any questions.
Any questions, Brian?
Hi, Brian Day, NASA Survey. I've heard some debate about the nature of tsunamis from ocean impacts and the threat they pose. And you can model the heck out of that, but is anyone in your office taking a look at the surface of Mars now? And we now see tsunami scars on Mars from impacts in the ancient Northern Ocean on Mars, and those could be a really interesting ground truth.
So I didn't know that. That's very cool about Mars. So what I would propose is the work that we've done on tsunami impacts has been done closely with NOAA, who have those experts, and that would be a very interesting topic for further study, I think.
Wonderful.
Thank you.
Allow us to pull up Mars Trek sometime and show you some tsunami scars.
Very cool. Thank you.
Yeah, so of all of these asteroids that you're showing, how many actually have Earth orbit crossing orbits?
Well, all of these are, come within a certain, I think it's 220 million miles, which we think is too close. Okay, so you can tell by looking at them that a fraction of them have Earth-crossing orbits. Okay, it is a smaller amount, true, but we haven't found them all yet. So,
Okay, one more.
one more?
Hi, Flaviani Venditti, Arecibo Observatory. What is the status of NeoChem? And I know it's not going well, I think, and what is the alternative to meet the goal of discovering the 140 to 300 meter?
So the spacecraft that you mentioned is is proposed to be an on-orbit near IR mission that would be able to rapidly detect basically the whole catalog. NeoCam itself is under extended phase A development activities and funding, and I believe that there's hopes, but a decision hasn't been made yet.
Okay, thank you.
Thank you.
Okay,
Thank you.
thank you.
Thank you.